I said, my conclusion so far after all this calculation and discussion looks like my 530M is going to work because simply it matches or exceeds my area of steel required by this equation here, which is my design equation. It simply, even if after I check my actual D, still works. It is less than row balanced, which means it's not compression failure. It is more than area of steel minimum. And so, which means the 530M is going to work. Now, uh, so guys, by now we finish one side of my design. And I know some of you will get, mad. All after those calculation and discussion, it's only one side. Yes, we did. It is only ultimate limit state. Ultimate limit state. So now we are turning into serviceability limit state, which we refer to as SLS. If you're doing steel course, I bet you by now you know what does it mean SLS. I guess every beam you design, every steel beam you design, you simply have to check deflection. Yes or no?
Yes.
And when we say check deflection, what do we do exactly? Are we checking the failure? Not really. We're checking the beam in every day how much does it deflect. And so for concrete, we have to do the same thing. We have to look at another state of the beam, which is not really at the failure. However, it's every day, every day. And when we say every day, we're talking about stuff like deflection, cracking, and vibration. Deflection, cracking, and vibration. So guys, the thing is, I'll explain for you, in concrete, we do not check vibration. So this vibration here, typically, we don't do that, huh? Because concrete are bulky, heavy, and they have enough self-weight to damp any vibration. You never see any concrete floor that really vibrates. Really what vibrates is the steel floors. If you have a floor that's it's supported on steel beams, they are not as bulky as concrete beams, and they always shake. If you guys remember in Stangrad Center, between the east and west wing, there are bridges on every floor. Do you guys remember that, or you forget about it? Huh? What do you think? You still remember Stangrad Center
Yeah.
between on the second floor and third floor? There's a bridge. Go to this
Yeah.
bridge and you'll see. If you just stand on top of the bridge and just wait for a minute while somebody is moving, oh my God, just like vibrates. Same as in downtown in Prince Island. There is a cable bridge, and just go to this cable bridge and you will see it just shakes up and down, huh? Because of people motion and vibration. In concrete, as I said, for concrete beams, very, very bulky, very lots of dead load, and it doesn't vibrate too much, and we are not concerned. In a steel beam, I can tell you every single steel floor, you must check for vibration. Okay, let's see what else. Do we check deflection on concrete? Yes, we do. But I can tell you also concrete is very bulky in section. The moment of inertia is so big, which makes concrete deflection so little. And even if we do it, it's not as easy as steel. Steel is very simple. Let me remind you again the right equation. Probably all of you will remember this one. WL to the power 4. Sorry, no. 5 over 384, and then WL to the power 4 divided by EI. Do you guys remember this term? Did anybody still remember 5 over 384 WL to the power 4 divided by EI? What is this for? Any help?
Um, Moment of
If you guys don't know, then I have to talk to Corwin, because this is how you check the deflection for simple beam if your beam is steel, huh? So it's 5 over 384 multiplied by the load, multiplied by the span to the power 4 divided by the EI, which is the modulus of elasticity, and then the moment of inertia. Guys, why concrete deflection is so complicated than steel? Because simply the section is not one material. and at some point the section will be cracked. Concrete is working fully in compression, does nothing in tension, and you have tension bars. And so if you want to do that, it's very complicated, and typically we don't do that by hand. We typically use the software to find concrete deflection. If you guys remember the SAFI in assignment number 1, when I give you the frame, it just the SAFI will find deflection for you. We don't do that by hand because it's more complicated, because not one material. Moment of inertia of a composite section is not easy. So I'm not going to cover this in my class. So what I'm going to cover in my class, which is the most common one and most important one, is cracking. So I'm going to box this out so you guys know. In my class, there is only one item will be covered, which is cracking. So we will see if the cracks in my beam is acceptable or not acceptable. By the way, so you know, you try to be emotionally prepared. All concrete beams, they crack. All concrete beams, they crack. There is not a single concrete beam that doesn't crack. All of them, they crack, but the thing is, does the crack width, or is the crack width acceptable? Is it acceptable or not acceptable? It is too wide or too narrow. If it's too narrow, great, because simply it means we have less water ingress. But if there is wider cracks, then there's a problem. So let's agree, all concrete beams, they crack. The only thing we can do is control the crack width. Hopefully this is clear. So guys, you can see this is exactly what I wrote here. And then let's focus on cracks. So on cracks, this is the bottom. I'm going to zoom in here. Look at my screen, please. So you can see this is the bottom side of your beam. Remember, concrete cracks in tension, not in compression. Concrete cracks in tension. Our beam cracks on tension side. So I know tension is kind of complicated. Where is my neutral axe and where is my the crack ends? Again, for simplicity, we will say, you know what? Anything from half beam down has an issue, or may have an issue. Anything above the half of the beam, then this is in compression, and then we don't have to worry about it because compression closes the crack. Okay, and you can see this is the half of the beam. This line here is half of the beam. So, and you can see I label here H/2. H/2. Please mute yourself, because just makes here some noise. Thank you. Okay, so this line here, it is the half of the beam, and then you can see I labeled this one H/2. Really, our cracks will appear at the bottom half of our beam, and the way we treat them is a little bit different. You can see here this entire area below the center of your beam, I give it 2 colors. The color at the bottom, it's called in green. So you can see here in green, the bottom. So this is zone number 1. I give here some legend for you. So a green is, I call it zone number 1. And then the magenta is zone number 2. So zone 1, zone 2. Because we will deal with them differently in our check. Anybody has any questions so far? Okay, looks like there's nothing so far. Hello?
I do have a question.
Okay, go ahead, Diego.
Why did you say that all the beams will crack? Like, can you explain that?
Because when, do you remember? But that was so like so long time ago, when we make our concrete beam out of plain concrete, no rebar at all. When this beam will fail, it fails as soon as the stress on the bottom fibers becomes so little, just 3 MPa. Let me take it by number. If my beam is 25 MPa concrete in compression, so my beam will fail when the stress at the bottom fibers is only 3 MPa. Do you remember that?
Yes.
Okay, so this means the load or the moment that cracks your beam is very little. And remember, if your beam doesn't have any rebar, the cracking marks the failure of your beam. If your beam doesn't have any rebar, it means the cracking at the bottom fibers when the stress is equal to 3 MPa marks the end of the life of the beam. Yes or no?
Yes. So what you just said, that all the beams will crack, you mean when they don't have rebar?
By the way, whether you, for sure, why do we do rebar? To go from this very, very high, low level of load to fill your beam to another level of a higher level to fill your beam. If I don't provide any rebar in my beam, your beam will fail at a very mature age, because simply as soon as the stress in the bottom fibers goes into 3 MPa or arrives at 3 MPa, here we go. You start see the crack and the beam will immediately fail to the ground because there is nothing holding your beam up. Okay? And this something is not acceptable. We're not really using the best of our material, because it's concrete is fantastic in compression, very bad in tension, and if we let it without any rebar, your beam will fail at a very, very early load. And that's the reason we add some rebar. What happens is when you add some rebar, even the stress in the bottom fibers arrives at 3 MPa, but still, so the crack will start to show. But since you have rebar going through, so this will hold your beam up. Does it make sense? So which means all the beams are cracked, but the cracks are very hair cracks, and that's why we don't see them. They are very, very little cracks. If the beam is loaded all the way to when the rebar yields, then the cracks will get wider and wider and wider until you see the failure. Did I help you out? Does this make sense for you?
Yeah,
Did I
absolutely.
answer you?
Yeah.
Jerry, she has her hands on. Up.
Yeah, sir. When you say all the beam cracks, you're saying that you're saying that uh even if it is reinforced, all beams cracks, right?
Yes, of course. Every
Yeah.
single beam, every single reinforced concrete will crack, but the crack is they are hair cracks.
They
And as
are
I said,
controllable.
what I said is in this part of the our check, we will just make sure that the crack width is not so big, so we have a control over the crack width.
So that h/2 there, can you please explain it again? That h/2, is that h/2 the length of the crack?
You know, the depth of the crack, so it's supposed to be from the bottom, because we know the crack will start from the bottom and will keep going up until one point. This one point is not easy, I can tell you, because simply concrete, it has a little bit of tensile resistance, which means it's kind of complicated, and that's why the code trying to make our life easy and ask us to use the half of your beam. If you are interested, again, come see me on one-on-one, and I will show you. It's not really easy discussion to know where exactly the crack will stop.
Well, nobody can tell that one anyway.
No, you can tell, but it requires a lot of calculation. Like I can show you, like let's say here is your the side view of your beam, okay? And so here is the center line. So what you see here is a side view, no cross section, huh? So here is a support. Let's say here is support here, and here is support here. Okay, and we're applying load. So what happened is we know that the crack will happen at the very bottom, but until where it's going to stop, it stops somewhere here, okay? Because every, like, you know, let's say this is my neutral axe, okay? Let's say this neutral axe, okay? And then at neutral axe, there is no stress and there is no strain. So the stress here, okay, is equal to 0. And then above neutral axe is compression. So concrete is fantastic compression. So my crack will never go to the compression side. It will go only to tension side. But if I leave it here, what do you think? It means concrete does nothing in tension, like 0 in tension. However, it does a little bit, which means your crack will go and stop here. So the stress at this point here, it will be 3 MPa, which is, let's say, F sub R, the modulus of rupture. But to find exactly where is this point in cross-section is not easy, as I said. And that's why the code is trying to make our life easy and simply say, okay, you know what? Take half of your beam. Half of your beam will be in problem, below half of your beam, the below part, because simply we'll assume that everything here is in tension. Does this make sense for you? Are you following?
Yeah.
Okay,
Thank you.
so no problem. So guys, listen. So guys, since we split our below half of our beam into two colors, two zones, and we will deal with them differently. We will check them differently. So what happens here if your beam is not that deep, and the number we're gonna do some reading in the code, but the number is 750 mils. If your beam is anywhere less than 750 mil, it means your beam is not that deep. And guess what? It means this area is minimum and it doesn't require any check from us. So zone number 2, and we will read this in the code. We do it only if H is more than 750. So if my beam is 800 or 850 or 900, then we have to choose, or sorry, check beam zone number 2. Zone number 1, we will do it no matter what. So every time we'll check zone number 1. Is that clear so far? Zone number 1 all the time. Zone number 2 only if the beam depth is more or greater than 750. If it's less than 750 or equal, then we don't have to check the side or don't have to provide any scan reinforcement. Now, guys, this is part of the code. So this part of the code here, it simply talk about the crack control parameter. So that's zone number 1. Look at the title. I said here, check zone number 1 or zone number 1 check. So this discussion here will tell you how do we check zone number 1. For the sake of time, I typically leave the students to read and enjoy the reading of the code, but I will save your time and I will go ahead and explain how do we do that. So in zone number 1, all we have to do is simply estimate this number here. So this number, this number, we estimate the Z. And Z, it's called crack control parameter. Crack control parameter. And so I'm going to show you how in a minute, but for now, I'm going to give you the big picture. The big picture is we find something called Z. What is Z? It is called crack control parameter. And guess what? The crack width is in proportional to this Z. So if the Z is so big, then the crack width is so big. When the Z is too small, then the crack width is too small. And so how do we control the cracks in zone number 1? Is by estimating the crack control factor Z, and then we put a limit on it to make sure that my crack is not so wide. And this limit is here. So you can see it doesn't exceed, the code says, doesn't exceed this number or this number. It depends on where is your beam. If your beam is inside the building, completely protected, then I can go and make sure that my Z is less than 30,000. And if my beam is outside beam and it's exposed to the freeze and thaw and all the bad things, then we simply should protect our beam better, and we should control much our crack width and make sure that my crack width is so small. And that's where this number is. We need to compare our Z to not 30,000. 30,000 is for interior beam. However, for exterior beam, we should maintain 25,000, less than 25,000. Otherwise, if the Z factor or the crack control factor exceeds this number or this number, what happens is it means my crack is so wide and it will cause problem to the performance of my beam on the long term, because there's lots of vapor and lots of water get in and simply corroded my rebar. Now, really what I wanted to show you is how do we estimate the Z, okay? So number 1, let's go and zoom in. What is the Z? So Z is equal to F sub S multiplied by D sub C multiplied by A to the power 1/3. So the simplest thing I can tell you right now is Fs. So the Fs, it's the stress in your rebar. The F sub S is the stress in your rebar, and the code says here, I'm going to show you, the code says the FS, I'm going to mark it for you, FS may be taken as 60%. The FS, it may be taken as 60% of F yield. You guys read that? The FS may be taken as 60% of F yield, which means If my F field is 400, then the FS is equal to 60% of 400, so this is equal to 240, yeah, 240. And then how do we find the A and DC? Let's go here and show you. So guys, you can see this is another table from the code where it's you have a graphical representation to show you what is A and what is D sub C. Remember, here is my formula. The Z is equal to Fs. So this guy is easy, huh? This guy is very easy, is equal to 60%, so 0.6 multiplied by 400. So this is equal to 240 MBA. Very easy, very simple. That's always the time, huh? All the time, your Fs equal to 240 MBA. So now all I have to do is show you what is DC and what is A. And what happened is, let's go one by one. Number one, A. What is A? You can see the division here. A is the shaded area divided by number of bars. A, capital A, is the shaded area, which is the area surrounding the flexure bars, divided by the number of bars. So what you have to do is, you have to find the centroid. So this is the centroid. This is the CG. So this one is the centroid, CG. And then after you find the centroid, which is marked by Y, you simply mirror around centroid. So you take the Y and double the Y. So for example, the centroid is 100 millimeter from the bottom. So this will be 100 plus 100. So that's one dimension of your shaded area. And then the other dimension is easy, which is from here to there. This dimension from here to there, we call it what? What do we call this dimension? Any help?
Beam.
What do we call this dimension?
Width of your beam.
Exactly. So which means, guys, in this equation here, I can write here 2y, 2 multiplied by y multiplied by b, which is the width of your beam. This is the area shaded, but you have to divide by the number of your bars. For this example here, can you count, please? 1, 2, 3, 4, 5, and 6. Huh? So we have 6 bars. So in this, what you have to do, you find the area of the shaded area, and then you divide by the number of the bars. So this will give you the A. Okay. Now, finally, what is D sub C? D sub C is here. So D sub C is here. And remember, D sub C, it is not the Y. Y is to the centroid, while D sub C is from the extreme fibers and tension to the first layer of rebar. To the first layer of rebar, which is, for example, is going to be the cover plus the stirrup plus half of a rebar, not to the centroid. Even if you have 10 layers of rebar, the DC will be the same. DC is to the first layer of rebar. Once you're able to figure out what is your DC, what is the A, and then you go through this math, you will find the Z, and then finally your Z has to be or less or equal 25,000 for exposed beam, and then 30,000 for not exposed, which means exterior and interior beams. Are you guys following? Okay, if you are, again, this is kind of a better picture, better representation. So what I did is here is I showed you if you have one layer of rebar and if you have 2 layers of rebar. Please read this slide on your own. It's just more explanation for you, and it's very critical to understand the difference between D sub C, which is always the last layer of rebar, and Y, which is your to the centroid. In this case, look at this case. When you have one layer, if you have one layer, your DC is equal to Y, because the centroid is here and the last layer is here. So the Y is equal to DC. So what's the area of the shaded part? Area equal B multiplied by 2DC, and then divide by 3. Why 3? Because we have 3 bars. Now, what if I have, let's say, 2 layers? Let's say 2 layers. So number 1, I have to find where is my CG, where is my centroid, and then multiply. I got D prime. I multiply D prime by 2, and then multiply by B, which is the width of your beam, and then finally divide by 5. Why 5? Because you can see my beam, it has 5 bars. That's how we find the A and the DC. Now, let's apply this by numbers. Let's apply this by number to what? To the problem that we started today. To this problem that we started today. Remember, Remember my beam today, probably I can draw for you very quickly. So the beam was this, and it is 400 white. Let me show you. So this is, I think I might know, I'm not, so I need to probably provide you some sketches here. So this is coming. So this number here, that's width of my beam, 450. Remember my beam for today, the width was 450. If you guys remember that. And then how many bars do we have? We have 5 bars. So 1, and then okay, we have 5 bars. So we have 5 bars. Anyway, it's just like cannot do that right now. So guys, the DC is equal to what? DC is equal to what? Again, from the bottom to the first layer of rebar. So that is going to be equal to the cover. I'm not sure how much was the cover. So then I have to go back to my slides. So it looks like the cover is 30, yeah? So
Yes.
DC is equal to 30 plus 10 mils for the stirrup plus 30 over 2 because my bar is 30 m. So this would be my DC. So how much is that? 15 plus 40, that's 55. So here we go. Here is my DC. And then as you can see, always the FS is 60% of my F yield. And then my A, since here I have one layer, it means my Y is equal to my DC. So you take your 55, you multiply by 2, and then you divide by 450, and this will give you the area around your rebar. And then don't forget, we have to divide by the number of bars, which is 5. And all you have to do is just push everything into the equation. And then what we got is 19,598. And what happened is this number is less than 25,000. And that's good because simply our beam is exterior beam and we pass our crack check. Now, can I do, or do I have to do skin reinforcement or zone number 2? What do you think, guys? In this problem here, should I do a check zone number 2?
If H is greater than 750,
Don't ask
then
me if.
yes.
Don't ask me if. It's already there. The problem is there. So that go back to that slide and see. And what you will see is our H is 900. If you guys remember that, so it's 900. And since my beam is greater than 750, it means
We
I
have to
need
check.
to. Not a choice, huh? You have to provide, check and provide, huh? And you can see it's going to be go different way. In zone number 1, it's a check. It's a check. It means there is a number I have to find, and this number has a limit. If number is below the limit, it means I'm okay. This is not the same way for zone number 2. Zone number 2, if your beam exceeds 750, we have to provide something called skin reinforcement. So we call those bars on the side. Let's go back to here. You guys remember my first class or first few classes, I talk about beam section and I said those are called main reinforcement in magenta, and those one in cyan, those are called skin reinforcement. So zone number 2, we're not finding any number. In zone number 2, since my beam exceeds 750, we have to provide skin reinforcement. So you guys, on your leisure time, you can read this one. Probably I can come back here in a few minutes. But the thing is, here is how we do the skin reinforcement. So the skin reinforcement is whenever my beam exceeds 750 mils, then I need to provide some reinforcement on the side. We call them skin reinforcement. So how do we find how much do I need? Do I need 1 bar, 2 bars, 3 bars? Let's watch how we do that. Number 1, you have to figure out what is the area that is being shaded right now. When you look up my screen, I show it here, it's shaded area, and even on my section up there, you can see this is where I talk about zone number 2, huh? So this area here, we need to find what is the area in pink, huh? This area here in pink, we have to find. which is a pure, it's a pure geometry calculation. It has no business with concrete. Guys, remember that from the bottom to the centroid, it is called D prime. And if you multiply times 2, this will give you the border of zone number 1. Do you agree? So basically, those numbers are known. In the previous example, this was 55 mil, so another 55 mil. So this dimension is 110. I'm going to mark it for you. So this dimension from here to there, which marks the end of zone number 1, this is 110, which is 2 multiplied by G prime. If this is 110, and remember, how much is H over 2? Does anybody remember how much? H is 900. So if H is 900, so H over 2 is 450.
450.
So this is 450. So let me ask you, if this is 110 and this is 450, can somebody tell me what is this dimension here from this point to this point here?
340.
That's very simple math, huh? It is 450 minus 110, so this is 340. So here we go. Now we know one dimension of the magenta area. So all we have to do is need to figure out what's the other dimension, which is from here to there, which is super simple. So what you have to do is look at the anatomy. So you can see from the face to that stirrup, how much is the cover? From the face in blue to the stirrup in red, that's the cover. And then we have 10 mil for the stirrup, and then finally we use half of the rebar, half of bar. So how much is that? So cover is 30, stirrup is 10, and we always use 15 m for skin reinforcement. So the skin reinforcement is 15 m. So 30 plus 10, that's 40, plus 7.5, what you get is 47.5. And guess what? This distance is twice. You kind of mirror, huh? You go from the face to the center of the skin reinforcement, then you mirror, which is means 2 times 47.5. So you will get a 95 mils. So this dimension is equal to 95. So now we know that we can find the area of the shaded part of zone number 2 by multiplying 340 times 95. Are you following so far? Are you following so far?
Yeah.
Yep, still writing notes.
Okay, thank you, sir. I cannot see you because I'm looking at my screen, huh? So guys, look at this. So here's the answer. So this is the last part of the problem. So you can see here, I figure out x. You can see here is x. I'm marking my x and y. So x is equal to 2 multiplied by the cover plus the stirrup plus half bar divided by 2. I got 95. How about the y? The y is equal to half of the beam, 900 divided by 2 minus 2 multiplied by DC. All of this comes from the geometry. Please, when you try to like make sense for this equation, just look here. Huh? Look on this side. There is no magic. Those are coming from this side here. Okay? And then finally, the area of zone number 2. The area of zone number 2, you just have to multiply x times y. You'll get 32,300 mil square of concrete. Finally, how much rebar? You guys learned in my class, there is something called reinforcement ratio, rho. So what is rho? Is a ratio between steel to concrete. So we know that. However, there's another rho. And rho is called, so there is a rho for the main reinforcement, the rho for the main reinforcement, and there is rho for the skin reinforcement. So this number comes from the code. I'll let you guys read it here. So I'm going to mark it for you quickly. So you can see here rho skin is equal to 0.008 for interior exposure. So if I have interior beam that is exposed to nothing and protected, then I need to provide reinforcement for skin equal to 0.8%. And if my beam is exterior, the same rho skin is equal to 1%. Okay, now let's go to the problem one more time. So my beam was, I think I made some mistake and I need to correct this one, because when I compare my number here, when I check the zone number 1, I compare it against 25,000. And the 25,000 is for exterior beam. And then let's see what's the header of the problem. Somewhere I wrote as exterior or interior. So guys, excuse me for that, and I will correct my slides. You can see my beam is exterior. So if my beam is exterior, it means my raw skin supposed to be, can you read? 1%. I apologize. In my calcs here, I used 0.008. So this is going to have to change, cross this one, and I will modify it and change it. So this one has to be 0.01. And what happened is, once you know that the skin reinforcement ratio, it's supposed to be 0.01, like 1%, then what you have to do is you come here, multiply the raw skin, which is 1%, like 0.01, you multiply by concrete area, and which is here. Remember, here is my concrete area. So very simple, what you get here is, you will get here, apologize, this number, it's supposed to be 323 millimeter square of rebar, which means, guys, which means what? Which means I need to provide 315M, because 215M doesn't do it, because 215M, if you go back to the table, to the chart, a 15M, a single 15M, I'm sorry, it will, sorry, because 115M is 200 mil square. 115M is 200 millimeter square, which means 2 is going to be 400. So still my answer still be the same. So this will be the answer. It means I will add 215M each side. Why each side? Because simply when I estimate this area, I estimate this area only, one side, and I multiply it by 1%. So I got 215M, and I have to do the same thing on the other side, another 215M. So this will be the answer. So there is a little mistake here, which is very simple. For exterior beam, so this has to change. This one is exterior beam. And so exterior beam, raw skin is 1% from the code. You take the 1%, you multiply by whatever the area of the hatched area or shaded area, you get here area of steel. For the skin, you convert the area of steel of skin to bar number. We typically use 15M. A 15M has 200. So if you divide 323 times 200 square mil for a 15M, you need 2 each side. Okay, guys, I guess we have 3 minutes. I want to say something, and probably I will say it one more time next class, is skin reinforcement can be used to help with the flexure capacity. You can see in this picture here, yes, they are not really at the very bottom, so their lever arm is way less than the main reinforcement, but you can use them in resisting the bending moment. So, and I know this discussion is not easy, and I'm gonna try it now. I'll do it next class. But sometimes me as a designer, I will never use them to resist the bending moment. I will just let them resist the shrinkage or the cracks on the side, but I will not use them in my design. Okay, guys, any questions so far?
Yeah, sir.
Okay, we have Jerry and then Domenico and then Diego. Go ahead.
Yeah, because regarding that skin reinforcement, I was just wondering, like, that those rebars cannot add will not affect the failure mode of the rebars, because it could add more, and then like, for example, your beam right now is in tensile, and then if you add those four rebars, then it might add, and then it might also.
Jelly, I got your point. I get your point. Thank you.
Yeah.
Amazing question. Amazing question. So Jelly is saying, if you're designing a beam and then simply you keep saying row, which is at the very bottom, this cannot be more than row balanced. So if we are very close to the row balanced, and if we come back and add a couple of bars each side, and I know they are little and their lever arm is not that much, and if you want to estimate it right, so you have to find the centroid. So this may turn you into a balanced failure. I completely agree, and that's why a good designer will not even use this. Look at this, please. Look at this picture here. So we talk about this one. A good designer will not even go to row balanced, will make a margin, will stop here, And I can tell you 75%. Some designer, they will not even go to 100% of raw balanced. They stay away from balanced by a 25% margin. For example, if raw balance equal 2.2, you multiply 2.2 by 75%, and this will be kind of their maximum. Does it make sense for you? Hello?
That's good.
Okay, Domenico.
Do we ever like talk? Like, don't the stirrups have anything to do with these equations? Because we're
zero in statics. Any perpendicular to forces, they don't affect each other. The plane of the stirrup is simply parallel to the bending moment. So the bending moment, the rebar is going this way, and your stirrup is going this way. The stirrup contributes nothing to the flexure resistance. Zero, nothing.
So it's just for like holding
for shear.
Okay.
For shear forces. For shear, when I teach you shear design, you will know how the stirrups will affect your shear capacity. For shear, not for bending. That's the reason why you add stirrups. Diego.
So when you calculate DC, if you have two different kinds of rebar in your main line, like a 25M and 20M, how would you calculate DC?
The lowest one.
The lowest?
Same as assignment number 3. If you have two different layers of a layer of rebar that had different sizes, like the assignment number 3, question number 1, on the corner there are two 25M and in the middle is a 20M. It is from the farthest, it is the closest rebar. So you go from the smallest diameter to the extreme fibers. Any other question, guys? Diego, do you still have question? Okay, guys, listen, we're done. I'm sorry if I went over time. Jelly, okay, go ahead.
Yeah, in terms of finding the number of the number of rebars for the skin reinforcement. If I have let's say 100, if I end up having 190, then I can just assume I only need one, right?
115M.
Yeah, 115M. So then if I have 450, then I could say I need 5 of those.
No, you need 3. If you have 450, then you divide by 200. It means 3.
I need 3. Yeah, I need 3. I need
yes,
3 of those.
You do.
Okay.
And by the way, probably I will need to go back to and show you one more time next week. But the code also said that the maximum spacing between somewhere here, the code says the maximum spacing should be 200. If you look at my slide, which again, we're going very quickly, so you can see the code also has some condition about the spacing between skin reinforcement, which is in this picture here. The spacing is simply from this line to the center of this bar. We need to check this to be 200, okay? But this is going to be next class. But for now, guys, any other question? Any other question for today? I'm sorry if I went more than I should, and we'll see you guys next class. Thank you so much.